Well, this is fantastic. I'm very happy to see you all here. I realize none of you know who I am, so I figured I would start off by telling you a little bit about me. My name's Chuck J. I am the, resident astrophotographer in the area. There are more of us, but we're kind of a rare breed. I figured I would start by telling you kind of how I got into the hobby, how I got interested in it, the types of equipment that we use. I obviously have a lot of different equipment here to talk about. If you have questions along the way, obviously feel free to stop me and ask. I'm more than happy to try to answer anything you have. I have always been interested in space. I'm sure most of you probably have too, being that you're here in the Astronomy Club. I remember growing up as a kid, I had the cutouts of all the planets hanging from the ceiling in my bedroom, and they were the old Voyager pictures, the flyby that happened in the late 70s. So they weren't as detailed as what you get these days, from New Horizons or Cassini or things like that. But I remember every day seeing those planets hanging there, and I remember quizzing my mother about the details of all the different planets, and she would get sick of it. And at the time, and this does tell you how long ago this was, the number of moons that we knew about around Saturn was 16. There's a lot more than that now. I think we're on probably hundreds of moons around Saturn that we know about now. So I grew up with that. I grew up watching Star Trek. I grew up watching Star Wars. All these sci-fi fantasy movies. I became a super nerd. And there's nothing wrong with that. You guys are all here. I'm guessing you're all the super nerds too. And that's cool. That's a good thing. I'm happy that you're all here like that, right? So, always interested in space, always looking at the sky, always picking out Orion, the Big Dipper, all the constellations that everybody knows about, My wife and I got married in 2011, and our honeymoon, we went to Hawaii. And does anybody know what's special about Hawaii with regard to space? It's one of them, yeah. There's a lot of really big telescopes in Hawaii on the mountain called Mauna Kea. It's a very high altitude. It's at a very low latitude. So it's more or less one of the most ideal places on the planet for observatories. Unfortunately, my wife has asthma, and they don't recommend going all the way to the summit if you have any kind of breathing problems, because the summit of Mauna Kea is about 14,000 feet high. But we did go to the visitor center, which is at about 9,200 feet. And they have daily stargazing there. And we showed up on the night that we decided to go, and there's like a ranger station there, and they have some telescopes set up in the parking lot so you can look through them. Some of them have screens that you can look through. But when we got there, we had to drive through the clouds. And when we got there, we were in the clouds. And I thought, wow, I can't believe the luck. Like the one day we picked to come to Mauna Kea, and it's cloudy. We live here in Pittsburgh. It's cloudy like 200 days out of the year or something like that. I come all the way to Hawaii where there's supposed to be beautiful weather all the time, and there's nothing but clouds. But fortunately, the ranger that was there said, well, don't worry about the clouds. We're going to go inside. We're going to watch a movie for about an hour about the mountain. And when we come back out, the clouds will have descended. And I thought, yeah, right. Yeah. So we went inside, we watched the movie, came back out, and I was shocked. When we came back out, the clouds were probably several hundred to 1,000 feet below us. And the sky was just pristine. One of the clearest skies I've ever seen in my life. When we went on this trip, I decided that I was going to buy a DSLR just for that trip, like one of these guys here, because I knew we were going to go to Mauna Kea, and I knew the skies were like I was seeing them at that point. So I had a tripod, I had the DSLR. That's all I had. I didn't have any extra gear, nothing fancy. I didn't even at that point really know what I was shooting at. I just aimed at the sky and opened the shutter. And I'm gonna show you some of the pictures that I got on that trip here. They're not great, but I still look at them fondly because I consider those to be my first astro pictures. And I don't consider that a serious attempt at astrophotography. I was, like I said, just pointing randomly at the sky, hoping to capture the sky. I didn't really get into the hobby again until maybe 6 years ago. My wife got me for Christmas a 114 millimeter reflector telescope. And she was very upset because when it showed up at the house, it was not inside another box. It was in a box that clearly labeled, hey, this is a Celestron telescope. So there was no surprise there. It showed up on the front door and I knew what I was getting for Christmas.
Which one is this big one? Or is
I actually don't have that one anymore. Okay. That one...
You can show one. Yeah.
That was a good first scope for visual astronomy. It came with a rudimentary, clock drive. So if you aligned it the right way, it would follow the sky more or less. It had a very, very bad tripod, so it was not very steady. But I can remember having to wait until New Year's Eve that year because, again, it was cloudy. But on New Year's Eve, we had a clear night. And it was freezing. It was so cold outside, probably -5. But I'm out there with this telescope and I'm trying to find things in the telescope, and I found Jupiter. And I could see Jupiter and I could see the moons, Ganymede, Io, the Galilean moons, that's what they're called. And I was transfixed. And it was interesting because even though the mount that I had would follow the sky, it's so far away and I was so zoomed in with the eyepiece I was using that almost as soon as I found it, it wandered out of my field of view again. And the same thing happened when I found Saturn. So a little while later, I got myself an 8-inch Celestron reflector. Mr. Gates told me you guys have one here that's similar. And that one got me better views of Jupiter and Saturn. But what I found then was that visual astronomy really wasn't what I was into. Because it's super cool. You look through the scope and you can see these worlds that are millions and millions and millions of miles away. But even with a scope that big, it's still kind of monochrome. It's not, you don't see the Cassini type photos where you can see the bands of color in Jupiter or the separation of the rings in Saturn. So I realized then that what I really wanted to do was photography. I wanted to take pictures because I wanted to show people the things that are out there to see. So I started, again, with the DSLR. Quickly, I graduated to a star tracker, which is what we have here. It's a little bit more sophisticated than a regular mount. It's basically similar to what my original Celestron had, but this is a little bit of a beefier model. You align it to the North Star, it follows the sky, and you could take longer exposures with your camera, to an extent. If I align very well with this guy, I can probably take up to about 1.5 minute exposure before it starts to trail, But that wasn't good enough for me. I wanted more. I got what they call aperture fever. So I went from a regular kit lens to this guy. This is a 250 millimeter refractor. It's called a Red Cat 51. I used this one primarily for a long time. Actually, not this specific one. This is a newer version of the Red Cat. The original one had a helical focus, or more like a camera lens, and that gets really annoying when you want to automate things. But I started with the Red Cat, and I used that for a long time. I went back to a 8-inch reflector from Celestron again. But what I found was that there's something probably wrong with the one that I had. I don't think Celestron scopes are usually as needy as this one was. It seemed like every time I took it out, I was fiddling with aligning the mirrors properly. You guys are familiar with reflector telescopes, right? You have to align the mirrors and get them in collimation to get a clear image. I spent so much time collimating that telescope that my precious hours of imaging time here in Pittsburgh were being squandered. I got so frustrated with it, I just decided to get rid of it, and I got myself a really big refractor. This one here is a 5-inch refractor. It's quite heavy, but it's It doesn't have the focal length that the reflector has. It doesn't have the aperture that the refractor has, but it is simple. I never have to worry about the lenses being in alignment. They're in their cell. They don't move. Probably the only time I'd have to worry about it is if I ever dropped it, you know. So I take it out, I put it in the yard, and I shoot whatever I'd like to have. The other thing that really, really becomes important when you're taking pictures, not so much for visual astronomy, but definitely for pictures, is the mount and the tripod. So tripods, you know, basic tripods like this, they're a little shaky. You know, if you get a little bit of wind, you know, your camera can start shaking and your images will be blurry. So shorter legs are probably better. Heavier is usually better. A lot of the mounts you get out there now, German equatorial mounts, things like that, they have really big, heavy steel tripods. And that's because they're heavy and they stay put. You put them there and they stay. They don't shake around. I recently upgraded from one of those German equatorial mounts to this guy here. And this is a strain wave mount. So German equatorial mounts work with a worm gear inside. And they rotate the worm gear, and the worm gear in turn turns the right ascension or the declination axis, you know, as it's commanded to. This one is a fundamentally different setup. There are two gears inside of each other, one of which is slightly flexible and has a slightly different number of teeth than the other gear. So as they rotate around each other, it causes the outer ring to move, and that's how you get the motion on the mount. And it's capable of carrying, for its size, way more payload. This whole mount here altogether weighs 20 pounds, maybe. But it can carry, if I add a counterweight to it here, it can carry up to 55 pounds. Whereas the German equatorial mount that I had, the mount head, the tripod, the counterweights for it, probably weighed closer to 90 pounds all said. And it would take me 3 trips to get it all out into the yard. And it can only carry 44 pounds. So this carries 11 more pounds, and it weighs about a quarter as much. So this technology is becoming much more popular, I think, you know, for relatively obvious reasons. But that said, I do use this refractor a lot. This is one of my go-tos. My other go-to is the Red Cat still, because sometimes I like to take a wide field shot, and a shorter focal length, like I said, 250 millimeters here, is much better. You get that wider view for larger objects, closer objects, things like that. This one's primarily like a galaxy hunter. So we're getting into the spring here, that's galaxy season, so you'll be able to see things like the Whirlpool, the Pinwheel, Bode's Galaxy, things like that. Those things are far enough away that a longer focal length is going to be better to catch those things. So yeah, the coming spring, I'll be out in my yard with this guy a lot, more than likely. So, any questions so far? Yeah.
You mentioned the weight of the tripods being heavier is helpful.
Mm-hmm.
Have you found any problems with this lighter version? Instead of the 90 pound?
I was worried that I would. That was one of my concerns when I upgraded to this thing. But I think the lighter tripod here, I don't know if you guys saw when you came in, this thing's actually made of carbon fiber. So it's very, very strong, but it's also very, very light. What I found is I think they've made up for the lack of weight by shortening the legs. The tripod for the equatorial mount that I had was probably about as tall as the top of the mount here. But as I mentioned before, it was heavy, it was steel, it didn't move. This one, obviously the tripod's a lot shorter, so the wiggle that you get is significantly reduced because the legs are shorter. But yeah, I have not seen a problem with this setup. I'm actually kind of in love with this mount here. It's my new baby.
I got a question in the...
Oh yeah.
Did your work give you the telescope, like that one and that one?
No. No. This is a labor of love. You know, it becomes an obsession. You know, if you love the sky like I do, and like I'm sure you do, I do very much encourage everybody to get involved in astrophotography. I think it's great. I think it's a great way to learn the sky. I think it's a great way to learn technology, but it can get pretty expensive. But one of the things that I wanted to talk to you guys about actually is that it doesn't really have to be that expensive. You can get started with just something like this. All this is a tripod for your cell phone. And I know you've all got cell phones. You just clamp your cell phone in there, hold it steady, and there are some different apps that you can get. I know on the iPhone there's an app called Photo Pills that people use. I'm not endorsing it myself. I've never used it. I can't explain to you how it works, but I do know it gives you more control over the camera than what the native phone app gives you. So you can tell it to take a longer exposure, 30 seconds, a minute, whatever you can handle. And you know, for the cost of that app and the cost of this tripod, you can actually probably take some decent wide field pictures of the night sky. So it doesn't have to be ridiculously expensive. Now, that said, it can be ridiculously expensive. This setup here, probably on the order total around $4 or $5 grand. And this is probably middle of the road as far as what you can have. There are mounts out there that will carry a lot more weight. There are telescopes that have much greater focal length, much bigger aperture, and they get very, very pricey very, very quickly. But the moral of the story is it doesn't have to be that expensive. You know, you can get one of these pretty cheap. Even if you wanted to go like a DSLR, you can find even a used one online pretty cheap. You know, and you don't need anything more fancy than the kit lens it comes with. That'll take decent pictures. People often ask, you know, what's the best camera? And the answer is the best camera is the one you have, right? Yes, there are better cameras out there. There's always better cameras out there. James Webb is out there floating in space. That's probably one of the best ones you're going to see. But most of us don't have $10 billion to spend on a space telescope, right?
Most of us.
So yeah, it's a great hobby, and it can get ridiculously expensive, but it doesn't have to. It also doesn't have to get ridiculously complicated. This guy here is a relatively new thing. It's called a C-Star, and it is an automated telescope and camera all in one. You connect to it with an app over Wi-Fi, or actually I think it uses Bluetooth. And it'll open up, it'll rotate itself around, it'll find whichever target you want to take a picture of, and it'll just start taking pictures. And what it does is what we do in astrophotography, we stack all the photos. I'll talk a little bit more about photo processing as we go, but it just starts taking pictures. Picture, 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 picture. Now, one of the problems that you run into is because this is not aligned to the North Star, right? It's what's called an alt-az mount. You guys know alt-az mounts, right? Anybody? No? Okay.
You might need to explain that one.
Okay, that's fine. So equatorial mounts are kind of like what you see here. It aligns to the North Star, and then it follows the right ascension axis through the sky. Alt-azimuth, altitude azimuth mounts like this guy just lay flat, and azimuth is this way and altitude is this way. So you can still find any target in the sky that you want, but as it follows through the sky, it's not aligned to the pole. So as that thing goes through the sky, from the telescope's perspective, it's going to start to rotate as it moves through the sky. So what the software on this guy is capable of doing is taking those slightly rotated images and rotating them back and then stacking them, which is pretty cool for like a tiny little device like that. You can get some pretty decent pictures out of that guy. My wife actually uses that one when she wants to do astrophotography with me.
What's the cost on that?
This guy right now, you can probably get him on sale around $400. So a lot cheaper than that. You know, a lot more expensive than the cell phone tripod, certainly. But it's, as far as starter devices go, I think it's pretty good. Yes?
What's it called again?
It's called a C-Star.
C-Star.
There's actually two different versions. This is the bigger version. This is the C-Star 50. They just came out with a C-Star 30, which is less expensive. I think it's like $300, $350. Slightly smaller sensor, I think, but just as capable. It does the same thing. It has an automated alt-az mount, go-to, you know. So pretty sweet. I'm not here to advertise. I'm just just telling you what's out there. Should we talk about photo processing? I'm sure you guys are curious about what things look like as I'm processing these things. So I actually have some images to show you. So, well, let's talk about how I started out. How about that? This is one of the first astro images I ever took. Yeah, that might help. Because these early images, I'll be the first to admit, they're not very good. So this is, if you can't tell, because I understand you can't tell, because again, it's not very good, this is the Pleiades. This is at the 250 millimeter focal length of the Red Cat there, and I was using a DSLR connected to it at the time. It's not great. I stack the images like you do. You get individual images that don't really show you what you think you're going to see always. I'm looking for a good comparison of what a single image looks like versus, oh, you know what, I think I forgot to throw that in here. I'll have to apologize for that. Anyway, a single image of what I take these days probably looks pretty much like that. This would be a single frame coming out of my camera, and I take a whole bunch of frames that look kind of like this. Then what I do is I stack them, and after I stack them, I can end up with something like that. So stacking the images, you use software to stack the images. The software can actually take an entire stack of images, analyze them all, align them properly so that they're all right on top of each other. And then one of the best things that it does is in each individual frame, there's some noise. You can see noise in pretty much any camera image you take if you zoom in far enough. It's the random red, green, and blue pixels that are assorted throughout the image that are just electronic noise from the camera sensor. What the software can do is analyze all that noise and see which pixels change from one frame to another and then help to average that noise out. It can also help average out things like satellites or airplanes that pass through your frame, because there's a lot of those these days. Thank you, Amazon and Starlink and all those companies that are launching thousands of satellites every day. The sky is getting polluted, and when you point a camera at it for several minutes at a time, it becomes more obvious because you start to see those trails in your images. But once you run your photos through the software, it can average all those out. So the final product removes all that, which I think is pretty cool, right? Couple of the things that I have to show you here. So I talked about Mauna Kea and seeing the sky from Mauna Kea. So this is one of the images that I took, 14-ish years ago. I had no idea what I was pointing at. You can see down here in the corner, there's the Pleiades. And I believe that's Jupiter, that real bright spot up there. Then I would move the camera and point a different direction and just take another picture. And in this one, now you can't really see it very well on the monitor here, and I can't even really see it very well on the screen that I'm looking at, but right around here is the Andromeda Galaxy. So you can see that, like, you know, if you take one picture, a lot of times one picture is not going to give you this beautiful view that, like, kind of like what we see above us, right? It just unfortunately doesn't work like that. You got to take a lot of pictures and then process them properly. Anybody see the aurora last year? Anybody take any pictures?
Yes.
Yeah? What's that? Not any good ones? Well, I mean, there's really not a bad picture, honestly. Did you see the glow in the picture? Well, then it was a good picture. This one, I'm a member of the Amateur Astronomers Association of Pittsburgh, the AAAP. This is one of their observatories in the area. This is over in Deer Lakes Park. It's called Wagman Observatory. So I drove over there back in October when the aurora was happening, and I got a few pictures with my DSLR. So that's what we're looking at here. This is just a single frame because if you stack images of the aurora, you end up with a big mess because the aurora kind of shifts over time. And if you stack all that on top of each other, number one, your software isn't really going to know what to do with it. And number two, it'll end up just a pink blur in the sky, which is kind of what it looks like anyway, but you see all the gradation as it goes through, and then you end up with the green down here. So that's good stuff. This was the first real picture I ever took of Andromeda. It's not super impressive, right? This was, I took this image, I think, 5 years ago, almost 6 years ago. No, probably about 5 years ago. But that's one I took just a few months ago. So you can see that, you know, as you practice, as you make improvements to your techniques, make improvements to your equipment, you can get a much more impressive result. And that's, I'm going to get a little, you know, adulty here. That's true of everything, right? If you're willing to put the effort in, you can get good at pretty much anything. So this is one of the things that I choose to put my effort into. And I think it pays off. It makes me happy. And I have actually won some awards in the annual astrophotography contest for the AAAP. Here's another example for you. This is the Horsehead Nebula. This is in the constellation Orion. This is actually the easternmost star in Orion's belt. And this image I took in 2020. The next one here was in 2021. And then this one was in 2022. So you can see more data, more time, more exposure time, and more practice gives you a much better result. Now, one of the major things that we deal with both in visual astronomy and in astrophotography is light pollution, right? I'm sure you guys have experienced light pollution. We live pretty close to a big city. There's a lot of light pollution around here. So I use different techniques for dealing with light pollution, most of which are filters.
You want the lights back up?
Yeah, for now. Thank you. So in my setup right here, I have a little filter drawer. There's a light pollution filter in there. And these things are some kind of dark magic. I don't know how they make these things. The companies that make these filters, they are able to reject the wavelengths of light specific to like mercury vapor streetlights, neon lights, things like that, while still letting through most of the light coming in from the sky. This is what's called a broadband filter. So this is the kind of filter that you would use for things like galaxies, reflection nebula, These are the things that are putting out pretty much all wavelengths of light, so you can capture with a broadband filter like this.
Does that go between the eyepiece and is that like a...
Yep. So it sits.
the eyepiece?
It sits in my imaging train here. So the lens cell is here. It comes down the tube through the focuser. I have a field flattener here, which we can talk about field flatteners if you'd like. But after the field flattener, it goes through this filter, and then it hits the sensor in my camera. And it just sits in there. I pretty much never even take that filter out of its housing. It just sits there permanently because this camera is what's called a one-shot color camera. This is pretty much exclusively useful for broadband targets. The opposite of broadband, anybody take a guess?
Single band.
Not single band, that's a good guess though.
Mono.
You use a monochrome camera with it, that's you're getting closer.
I'm out.
Well, what's the opposite of broad? Narrow. You do narrowband imaging. So in narrowband imaging, we use a monochrome camera, right? So this is a color camera. It'll pick up red, green, and blue all in one shot. This camera that I have here looks, for all the world, very similar to that camera. It's the same red cylinder, but this is a monochrome camera. It only picks up shades of gray. In front of that, I have a filter wheel. And inside that filter wheel, I have 7 filters. Individual filters for red, green, and blue. Also one for luminance, which is basically just a clear filter. It lets in any light that's out there to be gathered. And then I have narrowband filters. And narrowband filters are typically referred to as hydrogen alpha, sulfur 2, and oxygen 3. There are others out there that if you really want to get detailed, you can start using other ones. There's a hydrogen beta, and there's a magnesium one, and there's a whole bunch of different ones. But they're set up to allow a specific wavelength of light through the filter. So the broadband filter lets through everything except the mercury vapor street lamps and sodium vapor street lamps, things like that. The narrowband filter blocks everything except that specific wavelength of light. And there's different qualities of narrowband filters, and it's based on how wide that band pass is. Most of the higher end ones, you have a 3 nanometer wavelength band. So it'll be 650 to 653 nanometers it'll let through. Those are, I don't know if those are the actual numbers, I'm just throwing numbers out. These ones are 6 millimeter filters, so they're 6 nanometer filters, sorry. So they're a little bit wider, they let a little bit more light through, but they're also much less expensive. So what we do with narrowband images is we capture a whole lot of hydrogen data, a whole lot of sulfur data, and a whole lot of oxygen data, right?
That's just the class change.
Sure.
Good luck on your test.
Same, thanks for coming. So what do those wavelengths of light look like in real life, right? Pretty boring, honestly. Hydrogen alpha is a wavelength of red. It's a fairly deep red. Sulfur 2 is actually also a wavelength of red. It's just a slightly different wavelength of red. And then oxygen 3, it gives you some bluish green coloring. So what we do is we take all of those different data sets and we map them to red, green, and blue. NASA does this all the time with images from the Hubble telescope and also James Webb. They will take, it's called the Hubble palette. It's called SHO. So they take sulfur and map it to red, they take hydrogen and map it to green, and they take oxygen and map it to blue. And that's how you get a full color image using monochrome data. And I can do the same thing for broadband targets with a monochrome camera. I can use my red, green, and blue filters, and that's just visible red, visible green, and visible blue. A lot of people prefer to use monochrome cameras for astrophotography because you do technically get more data per shot. because it's an interesting phenomenon, right? If with the color camera, you have what's called a Bayer mask, and what that is all camera sensors basically are monochrome, how they're designed. It's either on or off. It's a digital. You catch a certain amount of photons for each pixel, and then that amount of photons is a shade of gray. But what color cameras have is this Bayer mask in front of the pixels. And in a square of pixels, you'll have red, green, green, blue. So all the electrons that are captured on this specific pixel are interpreted as red. All the electrons that are captured for these 2 pixels are green, and the last one is blue. So for a set of 4 pixels, you get 1 red, 2 green, and 1 blue, which is convenient. You're capturing all 3 at the same time, but you're also not getting as much data from each of those individual channels. And what you end up doing is capturing twice as much green data, but there's not a whole lot of stuff in space that's green. It's mostly red and a little bit of blue. So what you get with the monochrome camera is your entire sensor is capturing red, or the entire sensor is capturing green, the entire sensor is capturing blue. So instead of getting 1/4 of the data being red, you now have all the data being red. Or instead of 1/4 being blue, all of it's blue. And then you can assemble those later into a full color image.
Do you have images of like red, green, blue?
I do. Well,
Ones of something you've taken?
So the funny thing about using the red, green, and blue filters is the final product just looks like a regular image, right? But
like that was taken on red, green, and blue.
Yeah, this was actually taken with a one-shot color camera. Okay. So I was capturing red, green, and blue data all at the same time. I do have some narrowband images here, though. Let's see. I intentionally brought some narrowband so that I could show you. So here's the Sol Nebula. This is an emission nebula, which means that the gases in the nebula are being energized by the stars inside the nebula, and they're emitting light at different frequencies. This was captured with my narrowband images, and I used my hydrogen and my oxygen filters only. And the palette that was used here is called the HOO palette. So hydrogen is red, and then oxygen is both blue and green. So you end up with an image like this. Now, you can process data differently using different data. If you capture more data or different data, you can process it differently. This is the same object, but now it's primarily green, right? Because with this image, I used the SHO Hubble palette. So sulfur was mapped to red, hydrogen is mapped to green, and oxygen is mapped to blue. So because nebulae like this are primarily hydrogen, that's the most abundant thing in the universe, right, is hydrogen. You get a lot of red data from nebulae like this. But if you take that data, the hydrogen data that's normally red to the naked eye, and you map it to green, you end up with this. It's a much more green image. So if this isn't really what it looks like in real life, why would we want to look at it like this? Why do you think that might be useful?
Question.
Yeah.
It lets us know the makeup of gas.
Exactly. That's exactly why we do it. That's why NASA does this, because this allows us to see a lot of the finer structures, these pillars here and the clouds around the stars. It allows us to see a lot more of the detail in that nebula than we would see if we just took a visible light picture. Got some sharp kids here. I like it. So here's a fun one. This is the Pinwheel Galaxy. This is Messier 101. About 25 million light years away from us. This is in the constellation Ursa Major, so right around the tail of the Big Dipper. This is, again, galaxy season's coming up. This will be one of the ones that's readily visible. Have any of you ever seen a supernova?
See images. Obviously. Not the actual number.
I could show you one. So this image was taken in 2021. And the part that you'll want to pay attention to, now I apologize in advance, the next image I'm going to show you is rotated a little bit, so it's going to be a little bit difficult to follow which part of the image we're talking about. But right around here, this arm of the galaxy is where we want to pay attention. Because if we go to the next picture, here's that same arm of the galaxy coming around here. It's this bright spot right here. It wasn't there before. See? That supernova showed up in 2023. I believe in October, maybe? No, this was in May. And it lasted for a couple of weeks. It was visible. If you take a picture of M101 now, you can't see that anymore. It's faded. But this is a star blowing up 25 million light years away from us. And it's so bright that it looks like it's incredible. That star blowing up was probably bigger than our entire solar system, which is, it's mind-boggling, right? I mean, the size of things in space are just incredible.
Did you know that it was going to be there?
When I knew when I took this picture that it was there, yes.
Okay.
I didn't know, a couple of weeks before that. No, I had no idea.
Because usually they get like the alerts.
So when
like, the neutrinos come and
well, yeah, NASA's always watching the sky, but this actually, the first I heard about this was I follow a YouTube channel called Astro Backyard, and the guy who runs that channel was at a star party in, I want to say, Texas, and they were actually some of the first people to photograph this supernova, the people at that star party. It was fascinating to me. Here's another thing that I think is mind-boggling. So I mentioned that this is 25 million light years away, right? So the photons leaving this supernova were generated 25 million years ago. They've been traveling through space, towards Earth, through our atmosphere, through the lens of my telescope, to my camera sensor, right? 25 million years. So this happened, from our perspective, 25 million years ago. From the photon's perspective, that trip was instantaneous. Does anybody know why? Those photons left that supernova and hit my telescope sensor the next instant.
Relativity.
yep.
Special
Time
relativity. Yep. So we're familiar with Einstein, right? E equals mc squared and all that. As you get closer to the speed of light, time slows down, right? So, you ever seen the movie Interstellar? Yeah? And time differences and being closer to a gravity well and all that. That's real. That's not science fiction. That's real. So, for something that travels at the speed of light, there is no time. Time doesn't pass. And the only thing that we know of in the universe that travels at the speed of light are photons. Photons travel at the speed of light. So for that photon traveling from that supernova to hit my camera sensor, time did not pass. So there was no time between those two events. Supernova camera, done.
Because the distance was zero.
Well, the distance wasn't zero.
Not zero, but
It was 25 light years.
yeah.
But the time was zero. But from our perspective as an outside observer, that photon took 25 million years to get here. That is mind-blowing to me. And I hope it is to you guys too, because stuff like that is great. It helps you flex that muscle in your skull.
What's your job again?
My job?
Mhm.
I'm an engineer by training. I work on computer networks for the Navy
Okay.
these days. Computer engineer by training. So actually, that's a good segue into another topic of discussion. Question?
It was kind of related to that. It's just like because you do the like photo taking of the stars and you also like run it through.
Mm-hmm.
Is the technology more interesting than the space, or?
That's a good question. The short answer is no. I don't think the technology is more interesting than the space, but it's close. There's always, new cameras, new mounts, new filters, new controllers. One of the things I didn't talk about is this guy here, this little red box. This is called an ASI Air. It's basically a Raspberry Pi. You guys know what a Raspberry Pi is? A little single board computer. That Raspberry Pi in there runs software that controls this whole rig, and it communicates with my iPad here. So from my iPad, I can tell the mount to rotate in any direction. I can tell the focuser to extend, whatever. There's an automatic focuser here. That's this guy. So this thing will, it's actually really cool. So I put this out in my yard and I point it roughly north, right, towards the North Star. Because you guys know that the sky rotates roughly around the North Star, right? So I point this north, and then this thing has a routine on it to do what's called a polar alignment. So I point it basically at Polaris. It takes a picture of the sky, and it says, "Okay, I know where I'm pointing now." And then it rotates 60 degrees, and then it takes another picture. And it does what's called plate solving. It figures out what stars it's looking at, where it's pointing in the sky. And from comparing those two pictures, it can tell me how far off of the celestial pole I am. So once it knows that, it tells me how far off I am, and then I can use these bolts on the mount to make adjustments. So I use these bolts here to adjust azimuth, like that. Back and forth, and then this one on the back here will adjust altitude. And then when I think I'm close, I tell it to take another picture, and it does another comparison, and it tells me how far off I am. So the goal is to get as close as possible to that North Celestial Pole. Why is that important, do you think?
You don't want to have trail images.
Yeah.
You don't want to have visible motion, right?
That's exactly right. The closer we are to be aligned perfectly to the North Celestial Pole, the less chance there's going to be that the sky is going to move in a way that's different than the way the mount is moving. So the closer we are to that point, the better off we're going to be for our long exposures. Yeah.
So does it take like more than just like a second to take a picture then?
Oh yeah, yeah.
So you have to just sit there and wait?
Well, that's the other nice thing about having, the iPad connection to this guy. So I put this guy out in the yard, and after I do my initial polar alignment, where I actually have to manipulate the stuff on the mount to get it right, I go back inside. I can sit in my living room, and then my iPad here will show me, what the sky looks like, where it's looking. I can control the focuser from here. I can control the movement of the mount. I can tell it which target I want to go look at. So after I've done my polar alignment, now it knows which part of the sky it's looking at. And it has started tracking in sidereal motion, basically the motion of the sky. So from our perspective, very, very slow. It's not a quick thing. But it's following the sky, and it's waiting for me to tell it what I want to go look at. So if I say, I want to go look at the Andromeda Galaxy, I tell it, okay, well, I'm going to go look at M31. And it goes, oh, okay. And then it points roughly at M31. It'll take a picture, and it does another plate solve. And it says, okay, am I actually pointed at Andromeda? Usually on the first try, no. So it'll make another slight adjustment, and then it'll take another picture, do another plate solve, and then it says, okay, my target is centered. I got it. Now I'm going to follow it through the sky.
And how long does that take?
A couple minutes.
Oh, okay.
Yeah, it's pretty quick.
I don't know if that was like an hour you had to wait each time.
Oh, no, nothing like that. And then the other thing that we've got here is a second smaller telescope with a second smaller camera. Any idea why I have another one of these guys here? So as this thing is aligned to the North Pole, and it's following Andromeda through the sky, we'll say, right? Machines aren't perfect. You know, as good as these mounts are, and I do think this is a very good mount, it's not perfect. So over time, there would be a little bit of drift, one direction or another, you know. So what this is here for is for guiding. And what this will do is this camera, through this smaller telescope, will look at the same part of the sky. And it will find a star to focus on. And it will follow the motion of that star. Because there will be a little bit of motion because the mount's not perfect, right? So as that star moves relative to the scope, it'll feed information back to the mount to say, hey, you need to correct a little bit this way, correct a little bit that way. And with that, I can take 5-10 minute long exposures and still have very precise, very clear stars. No drift, just, you know, it does all the correction for me. So I leave this thing out in my yard overnight, it does its thing, it follows through the sky. As it gets to a certain point, you know, as things come up in the east, we'll say that way's east, right? I have a bunch of trees in my backyard, which is kind of annoying. But once my target clears the trees, this thing can see it and it follows it through the sky all the way to the zenith, right? After that, this part of the telescope is getting real close to the tripod down here. We don't like that because you have collisions, it can do damage to the equipment. So at that point, this thing does what's called a meridian flip. So it will go from looking like this and rotate around so that it's looking like this. And then it'll follow through the rest of the sky this way to the west. And it does that all automatically. I don't even have to do anything with it. Every so often through the night, as the temperature changes, it'll do an autofocus. So what it will do is it'll stop the main imaging sequence temporarily, and it'll start taking pictures of, I think, like 5 seconds at a time, just to get the shape of the stars. And it will zoom the focuser out a little bit, take a picture, zoom it in a little bit, take another picture, zoom it in, take a picture. And what it does is it plots everything on a graph, the size of the star versus the focuser position. And what you end up with is a V-shaped plot. And at the bottom of that V-shaped plot is where your focus point is, because that's where the stars appear the smallest. So that's where you want to focus. And that's what it does. It figures out where that bottom point is, it uses that as the focal point, and then it starts taking pictures again. Again, all automatic. It's fantastic. Now, when I started, things weren't that easy. This mount, like I said, I can tell it where I want to look, and it just goes and points at it for me. It's great. I can find anything in the sky, even if it's a really, really dim object that you cannot see with the naked eye. When I started, I had a tripod, maybe I had this star tracker. Everything I had to find was manual, right? So some things are easy. The Pleiades, you can see those really easily. The Orion Nebula, you can see really easily. You can see those things with the naked eye, right? But I wanted to take pictures of other things that I couldn't really see. You know, Andromeda. You know, in the light polluted skies we have here, you can't really see Andromeda with the naked eye. But I know it's there, right? Same thing with the Whirlpool Galaxy. I know it's out there, but you have to find it. And without having go-to functionality, that's all manual. You have to adjust everything manually and go find those things. So when I was out here taking pictures when I first got started, some things were very easy. I showed you my initial pictures of the Pleiades. Like I said, those were simple. But here is my first picture of the Whirlpool. This is Messier 51. I cannot tell you how ecstatic I felt when I finally found that guy in my field of view. It was fantastic because I had been trying night after night after night for hours at a time, and I could not find it. I just kept failing. I kept failing. And then one night I was out in my yard and I finally found it. I actually danced around in my backyard celebrating that I'd finally found this galaxy that I knew was there. I was pointed at the right part of the sky. I knew it was there, and I still couldn't find it.
And that was just all manual adjust?
It was all manual go-to. Yeah, I just, you take a picture because you can't see it with the naked eye. Mm-hmm. So I put it where I think it's going to be. I take a picture, 30 seconds, a minute, you wait, you get that picture. Nope, it's not there. Got to adjust it a little more. Take another picture. You got to wait a minute. Look at the picture. Nope, still don't have it. So literally hours I spent trying to find that target. I was so happy when I finally found it. This is the most recent picture I took of that same target. So again, this is the equipment that I used for that. This scope. I don't think I actually had this mount yet when I took that picture, but I had my other German equatorial mount at the time. But with the automatic go-to and the tracking, the auto guiding, all that stuff, it was so much simpler. I didn't have to spend hours searching for it. I just told my scope, hey, I want to look at the Whirlpool galaxy. And it said, there it is. Have fun. One of the other things that is really cool that is not directly related to astrophotography is just general photography. I got started, I did a lot of I do a lot of landscape pictures. So this is Glacier Bay up in Alaska. I've got, this is a place on the east coast of Iceland. So it's not just astro, but landscapes are another great photography hobby. Landscapes are a lot easier. They don't move. You don't have to go find them. They're just there. All it takes is a little bit of fiddling with some camera settings, and that's all. But one of the favorite things that I ever took a picture of was actually in my own backyard. And this was Thanksgiving morning a couple of years ago. I had been shooting from the backyard the night before, and I was outside gathering up my equipment to bring it back inside. And I found a visitor. I don't know if you can see it in the trees there. That's a barred owl. I had heard this guy in my backyard while I was out shooting, setting everything up, getting ready for the night. I'd been hearing him for weeks. Hearing her, I don't know how you tell with owls. I've been hearing it for weeks. My wife and I call it Hootie. Been hearing it, never saw it. But I looked up, and in the trees in my backyard, there it was. And I thought, well, these cameras, that's what this is here. That's my actual Astro camera. That's not the kind of camera you use to take a picture of something like that. So I tried to take a couple pictures with my phone, and I wasn't really getting it. So I thought, well, maybe I could go inside and get my DSLR. So I went back in the house and came back out with my DSLR, and I got a little closer, and I got a little closer, and I got a little closer. I probably got about 20 feet away to about where the tree line is in my backyard. And I lost my footing, and I looked down at my feet to make sure that I knew where I was stepping. And by the time I looked back up, it was gone. I never even heard it leave. They're fantastic animals, just completely silent. But yeah, so you can find things like that too while you're out taking astro photos. So I guess the moral there is don't just look at the sky. The sky is cool, but so is all the other stuff around you. Anybody see any of the comets we've had lately?
When was the last one?
Well, the last one was Atlas. This one was Neowise. It's not showing up too great on the monitor here, but that was Neowise from back in 2020.
I think I caught that one on my phone.
This one is E3's ETF. And then the most recent one we just had last year was Tsuchinshan Atlas. Comets are an interesting problem for astrophotographers. They add a level of complexity because they move, right? We normally take pictures of galaxies and nebulae and the stars, and I mean, while the stars move, they move, because the Earth moves, right? So we have mounts that can counter that motion, and we can follow those things through the sky. But comets are a completely different beast. They move in relation to the stars, and they do so fairly quickly. If you take a couple of pictures of a comet separated by 5 minutes or so, it will be in a slightly different place. They move relatively quickly. So in order to take pictures of comets, we actually have to process the image twice. So the first time through, we stack all the images, we align the stars the way we normally do. So the stars look like this, right? They're nice pinpoint stars. But the comet is a big streak in the middle of the picture, right? So then we process all those same pictures again, but this time we center on the comet itself. So we stack all the pictures of the comet and we shift them so that the comet is always on top of itself in the pictures. And what we end up with is a nice picture of the comet, but the stars are all streaky. So then what we have to do is combine those two. We have to separate the stars out of the first image and the comet out of the second image and put them together. And
What software do you use to do that?
So I currently use a piece of software called PixInsight. It's pretty much the gold standard for astro images. Pretty much everybody I see processing, posting pictures online, that's the software that they use. There are alternatives. There's a software out there called Cyril that does a lot of the same stuff, but I believe Cyril is free, which is nice. Free is always everybody's favorite price, right? I used to use a combination of a piece of software called AstroPixel Processor and Photoshop. But PixInsight does all of the things those two pieces of software did in PixInsight itself. So I really only use PixInsight these days. And it has functionality built into it to isolate the comet, and stack it appropriately. And that brings up another topic for photos like this. This is a bit of an art in addition to being a science, right? So we capture, that's a bit blinding, sorry about that. We capture the photons in our little buckets. And then we process the images to bring out the details, to show what's there. That's the Crescent Nebula. But as we're doing that, as we're bringing out those details, you have to make a choice. Do you want to very accurately represent what is there? Or do you want to take kind of a more artistic approach? Do you want to try, like with the narrowband images, do you want to try different palettes? Do you want to combine the different color channels in different ways? So that's definitely a choice that has to be made. I personally try to make things as realistic as possible. With broadband images, that's easy. You just, you're increasing the signal to noise ratio in the images, doing your proper calibration. Well, that's another important topic to talk about for astrophotography. Calibrate the images properly, and then you just don't add any extraneous color or things like that. It's fairly easy to do. But with the narrowband images, it becomes more of a challenge because from the outset, you're already processing these images in a way that does not accurately reflect what this thing actually looks like, right? So like the Sol Nebula that we looked at before, it's not green. If you looked at it in real life, it would be red with little hints of blue here and there. So my personal preference when I process those narrowband images is to process them like the first Sol Nebula image I showed you, the HOO palette, because I think that probably gives you closest to the most realistic representation of what that would look like in space. The actual thing itself would look like. This is another image that was processed in the HOO palette. So you can see that it's mostly red, little hints of blue here and there. And then I actually used the other one close to this for my wallpaper. And this is actually an example of different focal lengths, right? So that first one, that first image was way zoomed in on the Crescent Nebula itself. So you could see maybe more detail in the nebula, but you kind of lose the surroundings of the nebula. Whereas this one, I used a much wider angle lens. I used this guy here, and you can get a lot more of the surroundings. And because I used narrowband filters for this, I also got all of the surrounding hydrogen data. And you can't see it too well up here, but there's a little bit of oxygen up in this corner here. But I was able to get that out, get that detail out of the background using those filters. And again, I tried to process it in such a way that this is more like what it would actually look like if you could see it with your naked eye. It's still not 100% accurate, but it's closer than if you use like Hubble's SHO palette, where you end up with all the green and stuff like that. If I were to process this image using that palette, this would mostly be green. And as we discussed, that's valuable for actually learning the structure of the nebula, learning the different, gas emission bands that are coming from that nebula. But if you're trying to make a picture, just a picture, I prefer to do it this way and try to be more realistic. I mentioned calibration a second ago, and that's actually a very important topic for astrophotography. There are 3 kinds of what we call calibration frames that I use when I make my images. The first one is called a bias frame. So you can't see too well on the projector here, but bias frames, we use those to calculate out the read noise from our sensors. So basically, what you're looking at here is the noise that my sensor makes just by operating. That's all that is. So I take a bunch of these.
You can
Sorry, buddy.
monitor.
What's that?
You can see it on your monitor a little.
Yeah, you can see some of the green speckles in here, So I take a series of these, I average them all together to get a master bias frame, and then I use that in my stack of images so that my software can subtract that noise out. The next one that we use is a dark frame. So cameras are electronic devices, obviously, right? Around the camera sensor, we have electronic circuits. And when those electronic circuits are in use, they heat up and they can give off photons. They give off stray photons. Usually in like infrared, heat. Sometimes visible, although if you're giving off visible photons, you've probably got big problems. You're probably also letting the smoke out at that point. But what happens is, just to the side of the camera sensor, in some cameras, not all, but in some cameras, you have an electronic circuit here right next to the sensor, and it's giving off all these extra photons, and you end up with this starburst pattern here. And if you don't average that out, then when you stack all of your images together, all of your images are going to have that in there. And that really, really degrades the quality of your final image. So we use dark frames to get rid of that. Now, a lot of the new cameras that are coming out, and this one here included, have changed the design of the sensor and the camera, so you don't actually have to take dark frames anymore. They don't have this phenomena. This phenomena is what we call amp glow. There's an operational amplifier off to the side here. That's what's giving off the extra photons. But these cameras are redesigned so that doesn't happen anymore. So I don't use dark frames on this camera anymore. This one over here, yeah, I definitely still need dark frames for this guy. In fact, I think this dark frame actually came from this camera. So you can see I think this is a 5-minute exposure. So over a 5-minute period, there's a lot of amp glow there that's being caught. And the last one that we use are called flat frames. Basically what you're looking at here is dust on my optics. Either on the outside lens here, or on my filter, or on the camera sensor itself. You can get little teeny tiny specks of dust. And what that does is it leads different parts of your image to be dark, as you can see here. So what we do is we take images of that dust, basically, so that the software can average those things out. I actually have a panel here, where I put it. Oh, here it is, right here. I actually built this myself. It's an electroluminescent panel, and basically what I do is I plug it in, I turn it on, and you see it glows. And it's a very, very evenly lit white surface. So after I've imaged for a night, I take my scope, I point it straight up in the air, and I set this on top. And I take pictures of this. And because it's out of focus, you don't see this. All you see is white. But what that does is it brings out all of these dust motes. So I can take pictures of those. And then I can average all that out. Since I built this...
So you don't clean the dust, you just take it out of your image.
Yeah, exactly. Yeah, and unless it's like really, really bad. Best practice is not to touch your lenses. You know, you don't want to do that. Yeah. Sometimes with like an air puffer, you know, one of those little like rubber bulbs, you know, you can blow the dust off that way. But definitely don't use compressed air. Don't blow on it with your mouth.
Wipe.
Yeah, wipes are not usually good because you can just like grind the dirt into the lens. Oh. So yeah, that's no bueno. But yeah, since I built this, companies have actually started making these almost exactly the same thing. So I feel like maybe I missed an opportunity.
I think you did.
But being the engineer that I am, it was fun to tinker and, you know, come up with a solution on my own. And it is somewhat gratifying to know that other people saw value in the same thing. Okay. So yeah, I take all of those images, I stack them together with my actual, what we call light frames, the actual data that I've captured overnight. And that's how I end up with these final images. And then once I have all the images stacked, I can use the software to remove any background gradients, which tend to happen, you know, if you're shooting close to the full moon. You know, one side of your frame is more illuminated than the other, so you end up with a lighting gradient across the image. The software can actually remove that. I have different pieces of software that are able to take the narrowband images that I've processed, and a lot of times with narrowband images, you end up with stars that are kind of funky colors, because stars generally are white, maybe a little bit of a bluish tint, maybe a little bit of a reddish tint. But a lot of times with narrowband images, you end up with stars that are like magenta, which is weird. Yeah.
How many images do you usually set?
Good question. It depends on the weather, really. I usually try to do 3-minute individual exposures. That seems to work about the best. Sometimes I'll go to 5 minutes. And it largely depends on what the weather's doing. If I have a full clear night, I can do, you know, maybe 60 to 72, maybe 84 5-minute images over the course of a night. If I have several clear nights in a row, I may do the same target for all of those nights and just gather all that extra data, because the more data you can gather, the better you can increase that signal to noise ratio and the better your image is going to be. So
is it one image for every so many minutes? Or?
Yes.
Okay.
Yep. I take, like if I'm doing 5-minute exposures, then in the course of an hour, I'll end up with 12 individual images. Obviously, shorter exposures, more images. Mm-hmm. So there's definitely trade-offs, depending on if you want more images of a shorter exposure or you want fewer images of a longer exposure. The software will handle those things differently, and you may end up with different results as far as like noise removal, that kind of thing, because it does take all of those images and averages them together. So if you have a larger data set to pull from, it can do a better job of averaging all that. That's a good question. Thank you. So yeah, the software can actually take the magenta stars that you get from those narrowband images and make them a more realistic color. Or there's actually manual processes you can do that as well. But yeah, it's a very deep rabbit hole if you want to start going down it. I obviously made the plunge. I'm happy I did. I enjoy this hobby very much. I would encourage you to get into it. I think it's very much worthwhile. Yeah.
What's the furthest back thing you've ever taken a picture of?
Oh, like the most distant thing? Oh, geez. I remember the distance. I don't remember the object. It was about 43 million light years. I think it was a galaxy. I'm trying to remember which galaxy it was. It's funny, I remember the number, but not the name. There's so many of them out there, though. And the deeper you go into space, the more galaxies you're going to find. It's almost impossible to take a picture of a swath of sky and not catch galaxies. Because while we can see all those stars out there, those stars are still in our galaxy. You have to look past those stars to see the other galaxies. Yeah, I know that the whirlpool and the pinwheel are about 25 million light years. Maybe
Was it an NGC?
it was probably an NGC. Yeah.
4731? I just asked for a galaxy at 43 million light years, and it came up with NGC 4731.
That number doesn't ring a bell, but I admire your approach. That's good. Yeah, it was beyond the Messier catalog. I can tell you that. But yeah, so, and obviously, if you have bigger scopes with a longer focal length, you can reach further out, which is why James Webb is looking back billions of years. It's a huge telescope, and it has the infrared sensors on it to be able to get that light that has decayed basically from the beginning of time. So yeah, I'm not going to capture anything like what James Webb's getting, at least not with the far reaches of the universe. When it turns its eyes towards nearer objects, I can say, oh yeah, I got that. But yeah, I'm sorry, I don't remember what the object was, but I remember it was about 43 million light years.
Awesome.
You guys have any more questions? We have a couple minutes before the bell, so.
Do you ever look at planets too?
That's a good question. I don't typically photograph planets. I know a lot of people that do. This equipment, as I have set up here, is not really geared toward planets, believe it or not. If you want to do planets, your best bet is probably a reflector, like what you guys have, the Celestron, with a Barlow lens, and a 2x or 3x Barlow lens, and then like a planetary type camera. The sensor on the cameras that I use is just too big. You need a smaller sensor with different size pixels. But yeah, I've tried to do pictures of like Mars with my setup here, and it was just a red dot. And it just, but that was a good question. Thank you.
Well, the bell's about to ring, so
Thank
I'd
you.
really like to thank you very much for coming.
Yeah, appreciate it.
I appreciate all of you being here. It's fantastic to see you here. I'm glad that so many of you are interested. Like, no, I was actually really excited to come here and talk to you guys today, and I'm very glad that I got to do it. So
Sounds to me like we could do another hour and a half.
I could certainly give it a shot. You got another question?
What inspired you to come do this?
So I've full disclosure, I've never given a presentation like this before, but I work with a guy who knows Mr. Gates, and they got to talking about space, and this guy that I work with was like, oh, hey, I got a guy.
I said, what are the odds of getting this guy? Come and check it out. He said, I'll talk to the guy.
And here I am.
And the guy is here.
Thank you very much. Appreciate it.
Thank you all for coming too.
Thank you.